Humans have been looking at the stars for hundreds of thousands of years, and it's literally been a matter of life and death to know the stars. We count on the stars to know navigation, time-telling, and agriculture. Now we know we're connected to the stars in a more fundamental way. Every atom in our bodies, every atom on Earth was produced either in the core of a star during nuclear reactions or produced during the death of a massive star at the end of its life. So we are tied to the universe, and it only makes sense that we'd want to know more about the universe. All right, so today we're going to talk about the interior of the sun and the nuclear reactions that take place inside of the sun. Right? So the sun is the source of light and life, right? We wouldn't be around here to talk about it if it wasn't for the sun. What powers the sun has been a question for scientists for many years. If you look at the sun, it may look like, oh, it's on fire, but that's not the source of energy of our sun. The sun is not producing energy by fire. In the late 1800s, the idea was that perhaps the sun is generating heat because it's contracting. Now, it's true when our sun became a star, it started out as a big cloud of gas and dust, and then it contracted and got hot, and eventually got hot enough in the core to begin nuclear reactions. But that's not the source of energy of our sun. That's not why the sun is shining. It's not because of gravitational contraction. The reason the sun is shining was discovered in the early 1900s by this gentleman who should look familiar to you guys, right? Albert Einstein. And in 1905, he put forth the theory of special relativity, which tells us that energy and mass are equivalent. So you may have seen this equation, right? E equals mc squared. So the E is the energy, the m is the mass, and the c is the speed of light. So what this tells us is that energy and mass are equivalent. You can get energy from mass. It doesn't tell us how to get energy from mass, but it tells us we can get energy from mass. Right? Energy and mass are equivalent. So what's happening inside of the sun is that the sun is converting mass into energy, and that is what is causing the sun to give us its energy. That's why the sun is shining so brightly. That's why we get so much radiation from it. The sun is converting mass into energy via nuclear fusion. Okay? So if you remember one thing about the sun, remember this, right? So you can tell your friends how the sun is producing energy. Before we talk about nuclear fusion in the sun, I want to talk a little bit about nuclear fission. The two are easily confused. Have you guys heard of nuclear fission? Yeah. Nuclear fission is when a larger nucleus splits into smaller pieces. So this is what happens, for example, in power plants or in nuclear weapons. So a larger nucleus is splitting into two smaller nuclei, and we're getting energy from that. Okay? So that is fission. That's not what's happening in the sun or in any other stars. What's happening in the sun is fusion. And this is when two smaller nuclei fuse together, and through that fusion, we get energy. Okay? Now, I know what you must be thinking right now. You're probably thinking how to fuse two protons together. Protons are positively charged, right? What happens if you start to bring two protons together? Yeah, they're going to push apart, right? They're going to repel because of the electromagnetic force. So how do you get two protons to stick together, to fuse? Well, the key is very high temperatures. High temperatures means high velocity, lots of motion. And in the interior of the sun's core, it's hot enough that protons can stick together. So if two protons are moving relative to one another at slow velocities, they're not going to be able to fuse. But if they're fast enough, we can get them to fuse. We have to overcome the electromagnetic force to get that to happen. Okay. So we need this large proton speed to get nuclear fusion. This barrier that the protons have to overcome, this electromagnetic repulsion, is called the Coulomb Barrier. So for any fusion to take place between protons, we need to overcome that Coulomb Barrier. Now you might be wondering too, how do protons stick together inside of the nucleus if they're positively charged? Protons inside the nucleus are held together by the strong force. So this is what's binding our protons and neutrons together. So once protons get close enough within the nucleus, they can be held together by the strong force, which is stronger than that electromagnetic force that causes them to repel. Okay? Okay. So this is the basic reaction that takes place inside of our sun and stars like our sun to create energy. What happens is you combine 4 protons to get 1 helium nucleus plus some energy. Now, this is really cool because what you're doing is alchemy. You're creating an entirely new element inside of the sun, right? So a couple things to keep in mind. I just don't want folks to get confused. The notation. So you'll see in the slides and in the textbook little protons represented by little spheres. A proton is the same as a hydrogen nucleus, H1. Okay, so those are the same thing. So 4 protons combined together to make helium-4. All right, so that's 2 protons, 2 neutrons. So helium-4 is the helium that we're used to dealing with on Earth. And of course, we also get some energy out of this reaction. This is the basic reaction. Okay? So I'm going to step us through the proton-proton chain. So imagine yourself in the core of the sun, and there's protons whizzing around all around you. This is where the reactions take place. So we're going to start out with 2 separate reactions, same reactions, but 2 of them happening at once. 2 protons, or 2 hydrogen nuclei, come together, they fuse, and they create heavy hydrogen. So in this case, a proton has been converted into a neutron. So we have heavy hydrogen, and we also get a couple other particles. We get a neutrino and a positron. Has anybody ever heard of a neutrino? We'll talk about neutrinos in a little bit. What about a positron? You heard of PET scanners in the hospital, perhaps? Yeah, a PET scanner is positron emission tomography. A positron is an electron's antiparticle. So when an electron and a positron meet, they annihilate, and you get 2 gamma rays streaming off of them. So for the application of positron emission tomography, what happens is somebody will generally have cancer, and they'll inject radioactive material that emits positrons tagged with sugar. And the cancer tumor sucks up the sugar and the radioactivity because it's tagged. And then as the radioactivity emits positrons, those positrons annihilate with electrons and then create gamma rays. So that's what the tube is that the patient is in. It's a gamma ray detector detecting those gamma rays coming off so they can isolate where in the body that tumor is, how big it is. So that's a practical application of positrons. Positrons are also coming out of the sun in this step 1 of the nuclear reaction. All right, the next step. Step 2. All right, so we have created 2 heavy hydrogens, and now those 2 heavy hydrogens are going to combine with another proton, right? So again, we have 2 separate reactions, same reaction. Heavy hydrogen combines with a proton, and this time we get a completely new element. We get helium-3, right? That's helium has 2 protons, 1 neutron. That's helium-3. Okay. So out of this, we had started with 4 protons, and right now we're stuck with 2 helium-3 nuclei. Right. So the next step, and the final step in the proton-proton chain, is the combination of those 2 helium-3 nuclei to create what we're looking for, helium-4, right? Stable hydrogen. Also off of that reaction, we get 2 protons. Anybody want to take a guess what's going to happen to those 2 protons next?
Step 1.
Exactly. So it's going to cycle right back to step 1. So that is the proton-proton chain. This is what is happening inside of our sun right now to create energy, and in stars like our sun. This is the source of the sun's energy, the proton-proton chain. All right, you don't have to write this down, but in case you're curious, this is the steps written out for you. The first step are those two hydrogens coming together to create heavy hydrogen, our positron and our neutrino. And then we have the heavy hydrogen joining with that proton to create helium-3 and some energy. And then finally, the helium-3s come together to create that stable helium, helium-4. Okay. Our sun is enormous. Every single second, our sun is fusing 600 million tons of hydrogen, right? And producing a lesser amount of helium every single second. Our sun's been doing this for 4.5 billion years, and it'll continue to do it for another 4.5 to 5 billion years. So what I'm showing you here is the mass of a hydrogen atom. That little u is just a unit of mass, like a kilogram or a gram, only it's much, much tinier. So the mass of a hydrogen atom, 1.007825, and then there's the mass of a helium atom. So what I'm going to do is I'm going to multiply the mass of the hydrogen by 4, because that's what's going into our proton-proton chain, right? 4 protons. All right, now I'm going to subtract off the mass of the helium atom, because the mass of those 4 protons is larger, right? And this is what I end up with. I end up with extra mass. What happens to this mass? It's converted to energy via E equals mc squared, right? So it's not a lot. It may not seem a lot to you. 0.71% of the mass of the initial hydrogen is converted into energy, all right? But just to do a simple calculation, again, you don't have to write this down, but if we convert just 1 kilogram of hydrogen in the sun to helium, we get enough energy to supply the entire United States for 2 weeks. So that's just that's a very, very small amount of material. So you can get an enormous gain in energy from a small amount of mass. The trick is you need enormous temperatures to do so, right? You need the core of a sun to generate this sort of energy. So right now our sun is pretty stable. When we get back from break, we'll talk about what will happen to the sun near the end of its life when it becomes a less stable star. But right now the sun is stable. So I want you to think about the nuclear core and what's happening inside the core with these nuclear reactions. So the nuclear reactions are generating pressure that pushes outward. The mass of the sun is pushing downward. So we have gravity pushing in and nuclear reaction pressure pushing out, right? Right now they're balanced for us. So you think about what happens if the nuclear reactions were to slow down. If the nuclear reactions were to slow down, gravity would start to win, right? And the core would contract. Well, when the core contracts, it gets hotter. What happens when it gets hotter? Those reactions are going to speed up again. So then we have the reaction pressure pushing out. So in this manner, the sun has got its own little built-in thermostat, all right? And the sun maintains an equilibrium. It's a stable star, for now at least. Okay? The sun is getting hotter over the billions of years. We take 4 protons and we convert that into 1 particle. So we have 4 particles going to 1. The result of this is that the core of the sun is shrinking. And if the core is shrinking, it's slowly getting hotter. Now, in 5 billion years or so, our sun will come to the end of its life. It will become an enormous red giant, and it will be the end of life for the solar system. But before that, things will get quite unpleasant on Earth. In about 2 to 3 billion years, because the sun is heating up, the oceans on Earth will boil away. It'll just be too hot. So if there are still humans around in a couple billion years, we'll have to find a home elsewhere, perhaps on one of Saturn's moons. It'll be too hot for us on Earth. I think this is really cool, just how long it takes light from the interior of our sun to reach the surface. You might recall that our sun is 8 light minutes away. So if something crazy happens on the sun right now, we don't know about it for 8 minutes, right? That's how long it takes light to travel from the sun to Earth. But the photons we're seeing right now, if we were to go outside and look at the sun, actually spent a much longer time traveling from the interior of the sun to the surface. They spent hundreds of thousands of years starting in the core, bumping into other stuff, electrons, other particles, and eventually they make their way out. So really, the photons we're seeing, if we go outside and look at the sun today, spent hundreds of thousands of years traveling from the core to reach us. This is a question I get a lot about stars and our sun. How the heck do you know what's happening inside of the sun? We've never been to the interior of the sun. It's not something we can take into our laboratory to dissect. We have to use other methods of studying the sun's interior. And the way we do that is we make math models, or we observe solar vibrations, or we observe the particles that are coming from the sun's interior, those solar neutrinos. Now, if you happen to be a computer person and you still want a career in astronomy, you can become a stellar modeler. These are people who write sophisticated computer code to simulate what's happening inside of stars. So the input will be physics equations for gravity, temperature, and energy transfer. And then the output will be properties of the star, like temperature, pressure, density, all as a function of depth within the star. We want our models to be better and better so that we can understand what's happening. And this is just like what a model might come out looking like. So we have temperature and density starting in the core where nuclear reactions are taking place, and then the zone outside of the core where radiation is heat transfer, and then the convection zone where convection is transferring heat. So stellar modelers will do this. They'll also predict the abundances of different elements in the stellar atmosphere, which is also a very interesting thing to do. Like I say, if you're a computer person, you want a career in astronomy, you can be a stellar modeler. We also study solar vibrations. This is helioseismology. And if you've ever taken a geology class, or if you know anything about geology, you know geologists will study earthquakes, the P waves and the S waves, to understand the density of material underneath Earth's surface. Solar vibrations is the same idea. Astronomers look at the surface of the sun and how it vibrates. So parts of it are moving in, parts of it are moving out. I don't know, do you guys remember what that is? How would we detect when something's moving away or when something is moving towards us? Blue shift and red shift, exactly. So they look at the Doppler shift of the surface of the sun for these fluctuations that originate deep inside the sun's interior to learn about the sun's interior. So that tells us things like density of the material underneath the surface. And finally, neutrinos. So neutrinos are teeny tiny particles that have mass, but they don't interact with very much. In fact, there's many of them right now streaming through our bodies, streaming through this room without interacting with anything. But they're generated inside the core of the sun. So they're like little messengers telling us about what's going on inside of the sun's core. So it'd be great if we could look at them. The problem is they don't interact with very much. So it's kind of like having like a pool strainer and trying to catch air, right? They're difficult to capture. If we can capture them, though, we can learn about what's happening in the sun's core. I want to talk a bit about the solar neutrino problem. It's been solved. I don't want anybody to panic that we still have a problem with our solar neutrinos. It has been solved, but it's a really interesting view of science working. Right. So in the 70s, the idea to detect neutrinos was to look for them in underground mines because they don't interact with much, and you don't want to be drowned out by the noise of other particles. Just like if you want to hear a pin drop, you don't listen for it in Times Square. You go to a very quiet space. Underground is a very quiet space to look for neutrinos. Neutrinos do interact rarely with chlorine. And when they interact with chlorine, they'll make argon, which is radioactive, and then you'll detect the radioactive argon. So what they did is they found a gold mine in South Dakota, and they filled a vat of cleaning fluid and looked for neutrinos, and they found them. They found some neutrinos in this gold mine. The problem was they didn't find the right number of neutrinos. Remember, we've got stellar modelers telling us how many neutrinos should be coming out. We have the physics telling us. The problem is there is a third of the number of neutrinos detected. This is a huge problem. So two solutions. Either we're completely wrong about what's happening inside the interior of the sun, and that would be pretty tragic to have to rethink all of our ideas of what's happening in the interior of stars. Or for some reason we're not detecting all of the neutrinos. And it turns out that was the solution to the solar neutrino problem. We were under-detecting the neutrinos because we didn't know there were 3 types of neutrinos. The mine in South Dakota was only detecting one type of neutrino. Now we do neutrino detection and we can find all 3 types. And I think this would be a really cool job. So again, if you want to be studying astronomy but you don't think you want to spend your days at an observatory, you can spend your days underground in a mine studying neutrinos. This particular neutrino detector is in Canada, and it's filled with ultra-pure water, and this is the back of little detectors. So inside, every once in a while, neutrino will interact with this water, produce a reaction, and the detectors can find it. Another facility is Super Kamiokande in Japan. And these bubbles alongside the wall, this is like a tank with, again, water in it. These bubbles are photomultiplier detectors. They detect radiation. And every once in a while, a neutrino interacts with that water. And what happens is you get a particle that moves faster than the speed of light in water. Not faster than the speed of light in a vacuum, because that would violate the rules of physics. But it's like a sonic boom for light. And when you get that sonic boom for light, it's called Cherenkov radiation, and it can be detected by these photomultiplier tubes. So Super Kamiokande can detect neutrinos in this manner. In 2001, they had an incident at Super K where one of these PMTs busted, and it set off a chain reaction, and like 6,600 of them busted. It's fixed now and ruggedized, but it was quite an expensive repair.